First thing, of course, I have to thank the organizers, Beat and Patrick, and for inviting me for a second time. Enjoyed it last year, this meeting, very much, and it has considerably grown and developed nicely. And having already been quoted as somebody who likes to compare drug delivery with taxi driving, I think it is, in a sense, it's true. It's depending on the passenger and depending on the territory where you have to drive. It's a different vehicle that you need if you want to bring an elegant lady in the evening to a theater, or if you have to deliver a crowd of hunters somewhere in the deserts to shoot elephants. It's a different car you need. And, well, the cargoes, the passengers might be not that different to that what we have been hearing before, but it's a different route of application. If I look through the program of this last session, I guess this is the only application of nanomedicines. This is not meant to be injected parenterally. It's either taken orally or perhaps administered rectally to reach the lumen of the intestinal tissue. So it's also not about cancer, it's not about cardiovascular disease, it's not about diseases that are really so severely killing people, but anyway, for the people who are concerned with Crohn's diseases, with inflammatory bowel diseases, they're quite suffering from them. The problem is because of the symptoms that include diarrhea, it's no easy treatment. Whatever you take, whatever you give orally, it doesn't stay at the site where you would like to have the treatment taking place. So you have to give it again and again. You give typically corticosteroids, that means you give too much than you would need to give. Actually, you get systemic absorption side effects and all these things. So wouldn't it be great if we had a possibility to target, just like typically in cancer, to the sites where the inflammation is and limit actually the action of the anti-inflammatory drugs to those areas of the tissue, and also reduce systemic side effects and keep it longer there. That actually, where you see in the date of this publication, some 10 years back, where Alf Lamprecht, at that time a graduate student, now he's a professor in Bonn actually, so doing quite well, he raised the hypothesis that if we could make particles smaller and smaller and smaller, and you see here when we reach the nano range indeed, there is by an EPR-like, but not exactly EPR effect. This is in the mucosal tissue, this is not in the endothelium or blood vessel, an accumulation of these particles. So the smaller the more, and selectively for the inflamed tissue. Well, that's nice to take a photomicrograph, a confocal laser microscope, and show that there is something fluorescent there, but it doesn't really do any good. So we went on together with colleagues in Japan and in Nancy to do some studies in a preclinical animal model actually, and to be very brief here, what you see are two advantages. Compared to the oral, to the solution of the same anti-inflammatory drug and the same dose, we saw a prolonged action. This is the solution that gets worse again after a few days, and this is the nanoparticles that stays in the state of alleviation of the symptoms for a longer period of time. So we get a better and prolonged actions for the nanoparticles, and at the same time we could observe a reduction of some central nervous side effects. If you don't treat the animals, then of course no side effects. If you treat them with the oral solution of the drug, you get a rather high adverse effect induced. If you take the nanoparticles, and at the same time for this prolonged action, you get a reduction of the side effects by about 50%. So this is nice, and this we should like to see in other species than in rats, but then the problem started. We had really troubles to take this into the clinic, regulatory difficulties, ethical difficulties, but since about 1.5 years we found collaborators ready in the University Hospital in Jena. We found the ethical committee ready to allow us a first study where we implied, or the doctors there actually did it, implying confocal laser endoscopy, which, like with a confocal microscope, allows you to take a Z-stack section and to see where the particles are. So we made some preparations and we tested micro and nanoparticles, and surprisingly, in the first place, I have to tell you, the nanoparticles we could never detect in any of these situations. Maybe it's a species and size difference between rats and man. But for man, it works in that sense that where you have inflammation, you see more particles than in the case where the tissue is healthier. You can even come up with a certain correlation between the degree of the severeness of the disease and the amount of particles that is accumulating there. So interesting, and maybe we can carry this on further. This is of course again the plastic bead fluorescent labeling status, so we have to go for incorporating something, but at the same time we were interested more what we can find out to explore the mechanisms to optimize the system. And as some of you know my lab, we like to work on cell and tissue based in vitro models. So together with or in the context of the EU project Meditrans, coordinated by Gerd Storm, our chairman, and in collaboration also partly with his group, we came up and developed a three-dimensional co-culture system of CACO2 cells, some of you know that, together with cells of the immune system. And in that system we could actually elicit an inflammation. So it's not a model of the healthy, but of the inflamed intestinal mucosa. And the advantage of these systems, well, here you see the situation, you see the system as such looks quite similar to the real thing. You can localize the immune competent cells in this system. And what you actually see on this graph is when you look for an immune response as a typical endpoint, we take the release of interleukin-8, you see the advantage of the co-culture compared to the single culture. CACO2 cells alone, they don't react that much, but if you do this co-culture, you get a very strong response of an inflammatory stimulus. So now you're in the situation that you can actually test anti-inflammatory drugs and drug delivery systems, and that we did together with Tuan Lammers, partly who is in the audience. He prepared in this context a liposomal system. We wanted to again evaluate the nanoparticulate system, both involving actually budesonide. We made the system in such a way that we could deliver the same dose. You see the problem with the liposomes is that you don't have such a high encapsulation rate by the physical chemical properties of these molecules. And the results were accordingly. So this is always the level of interleukin-8. You see in normal situation, you have a basic level of around 3 to 5. If you inflame the tissue, it goes up considerably. If you now treat the situation just with a solution of budesonide, you get an amelioration after 24 hours, but it goes back again after 48 hours. If you take the nanoparticles, you bring down the inflammation for one day and for another day, and with the liposomes, in this case, I must say, they don't seem to be that beneficial for this disease. The inflammation went up immediately. Probably it was too much of the lipids, which was not so nicely tolerated by the tissue here. As you can see, the liposomes are quite strongly interspersed in this system. So this is starting point where we are now, and we are luckily in the context of two new projects. So one will be that we are taking a new biotech anti-inflammatory drug. We want to have another look at interleukin-10. Have to be short here just to summarize. It is a promising candidate for a local therapy because it should actually work, were it not that if you are giving it systemically, there were a lot of problems related to systemic toxicity. So if we had a system to just bring it there by this technology, this actually should be an advantage compared to other systems. And we are now in the situation to develop delivery systems. It's not so easy because of the relatively limited stability of interleukin-10 during this nano-encapsulation process, and the technology that we are just about to start is a so-called nanospraying technology, which works via such a vibrating membrane, and it makes us nicely nanoparticles the size of 100 nanometers, which indeed are able to incorporate and release that drug. Very briefly also just to mention, we have started another project in this context called BIBA, so that's meant for biological barriers. In this context, Patrick Boisseau, you have been talking today, is the coordinator of this project together with CER, and there we want to explore few carriers, the nanoparticles of course, and the lipidots that you have been hearing before. We have a multidisciplinary team that also involves gastroenterologists and people in histology and so on, and I hope that during those lines we will further progress in this project. So having finished here, I hope, almost in 10 minutes, I would like to thank you for your kind attention. Thanks to our sponsors and my team that chose us last year on a sailing trip. And for those who like the in vitro approach, the cell culture models, please be invited to come to Saarland University to our 8th International Conference on Workshop on Biological Barriers next winter. Thank you very much.